Force and Newton's laws. First, we look at the law of inertia. Inertia is a concept that objects at rest stay at rest unless acted upon by another object. Or objects in motion move at a constant velocity unless acted upon by another object. Now, that gives us then the concept of force when an object acted upon by another does not stay at rest or does not move at a constant velocity. And this is Newton's second law, that the force will be defined as the mass of an object times its acceleration as a result of being acted upon by another object. And since we just introduced the concept of force, we need to look at units, right? It's a derived quantity, F equals ma. And so the square brackets here I use to mean the units of. So the units of force are the units of mass, the kilogram, times the units of acceleration, meter per square second. So we get units of force to be kilogram meter per square second, and that's called the Newton, just given a symbol capital N. So Newton is the unit of force in the meter kilogram second family of SI units. And there can be multiple forces, and we're going to look at some variety of forces, and there are two categories. There are the field forces, which are the fundamental forces of nature, which includes the force of gravity that near the surface of the Earth we call the force of gravity that the Earth exerts on an object, its weight. There are electric and magnetic forces, and not shown on the list are the nuclear forces, the so-called strong and weak force. Then there are contact forces that are like a macroscopic type picture, where the forces are actually electromagnetic in nature, but they involve physical contact. And we'll start with the tension, the normal force, and surface friction. Now, before we get into more about each of these types of forces, it is important to note that forces occur in pairs. And this is Newton's third law, the principle of action and reaction. And that's a confusing term, but all it really means is that in an isolated environment, that there can't be a net force acting on something, because that would mean it's not isolated. If we split that, whatever that is, into two pieces, A and B, then the idea is that if object A exerts a force on object B, then B must exert an equal and opposite force on A, so that when considered as a whole, AB, there's no net force. So two forces would cancel out then on A and B taken as a whole, but considering A or B separately, we get this action-reaction pair. So if B exerts a force on A, and I'm showing an arrow on A going to the right, then A exerts an equal and opposite force on B, where the red arrow on B then goes to the left. And I actually recommend that you label action-reaction pairs with the same label. You might have expected FA on B and FB on A, switching the order of AB and BA for each of these labels. But since the magnitudes of the forces are equal and only the directions are opposite and the arrows show the direction, I highly recommend that you label your forces with magnitudes. So there's no need to switch the A and B if you're representing a magnitude. Now, we could have, while a single force is a single action is used to define force, there can be multiple forces acting on an object. So it's somewhat implied that we can use the principle of superposition. In other words, if there's multiple forces acting on an object, the vector sum of those forces is what we would take as equaling the mass times acceleration of the object. Now, just to look at some details of some of these forces, here I'm showing, and we'll be doing numerous problems. Here's a ball on a string connected to the ceiling. I would have my weight. My object of interest is this ball, and the weight always acts vertically down to the earth. mg, mass of the object times little g, 9.8 meters per square second. Right, so that's the weight of an object. Tension, just using the letter T. Tension is always parallel to the string, pulling away from the object. Here's a couple more examples. Here's an incline, and the object of interest is a block on that incline. Again, I have my weight, mg, vertically down, but the surface, the surface force, there's a surface that pushes back. That pushback is called a normal force, and normal mathematically means perpendicular. Indeed, the normal force is perpendicular to the surface, pushing the object. And I like to use a funny looking N for the normal force, not to confuse that with the block N, the unit Newton. So I just use like a scripted or funny looking N that you'll see me use. Now, if the object is sliding down the incline, there would be another surface force, the friction. And if the object is sliding, it's kinetic or sliding friction, and I usually use a lowercase f subscript k. So F sub k is the kinetic friction force that the incline exerts on the block. If that block was initially sliding up the incline, maybe you pushed it up the incline before this picture began, before we looked at it, the friction force would then be going down the incline. The sliding friction force always attempts to slow you down. Now, another kind of friction is static friction. I could place a block on the incline, release from rest, and it just stays there. Right? So then, not only is there the pushback normal force perpendicular to the surface, but that there would be a static friction preventing the object from sliding. And for these forces we just looked at, here are some of the, let's collect these symbols and discuss. So weight, the force of gravity, mg. Tension, normally a capital T, parallel to the string, pulling away from the object. Normal force, funny looking N. It's always a push back at a surface, perpendicular to the surface, pushing into the object. Kinetic friction, if there is sliding of one object over another on the surface, F sub k, and we'll see that we will take that to be proportional to the normal force. So the friction and normal force at the surface are actually proportional to each other by mu sub k, the coefficient of friction. Coefficient of friction is usually just a decimal number less than 1, like 0.1, 0.15, 0.2. Now, static friction is similar, but a little different in that the actual static friction force could be anywhere within a range from 0 to a maximum possible value. And that maximum value is a coefficient of friction times the normal force. But here the subscript s for the static case.